Greetings everyone. In previous class we discussed about the concept. We begin to discuss about the concept of current in conductor. In that we realized first of all we have to understand the concept of free electron, so we can bring out the concept of current in a conductor. And then we have discussed what is free electron in a conductor. That was pretty much, we have explained by two methods. First was the band theory, right? And second one with the help of metallic bond. If you are forgetting what it is, you can go and watch previous video. And then we start to understand, after understanding this concept of free electron, then we begin to ask about current in a conductor. For that we brought three stages. First, conductor which is isolated. Second, conductor where it is surrounded by some electrical external. And thirdly, conductor where there is connected to a battery, right? That is our final stage. Here we will see some current. If you remember the previous two cases, even though in second case there was some electric field, but the net force on the electron was zero because conductor also played their induced electric field. Go watch all this in previous video to have more clarity. Otherwise, it can be a little confusing if you haven't watched the previous one. So we'll begin. So we'll have again in that we have already discussed few bits, I think, but I'll give you few like quick revision. So some part of things we have already discussed. I think we were on the discussion of drift velocity. So I'll give you a quick recap. So here we will have some conductor which will be connected to a battery. Right, and we'll draw some kernels. Right, and we will have some free electrons. Electron are also known as conductive electron. Okay? And remember the free electron density of metals or their order, because it is important. So if there is a battery, it will create its own electric field, that is electric field to battery, you can write TB for remember. And in this case, because there is electric field, like in previous case if you remember, even though there was some electric field, the net force on charge was zero because charge will get accumulated on one of the side and they will create their own electric field which will counter the external one. But here, because we have battery, so battery will not let it happen. The battery will prevent to accumulate all the electrons here. So what will happen? That electron will not have the chance to get accumulated, so the induced electric field by the conductor will be nearly zero. It won't be zero, it will be nearly zero, limit tends to zero. And in that case, your net force on electron will be non-zero, right? And you can think battery like a pump, or you can imagine a fountain where the pump does only one thing, that is pushing water outward, and again it sucks and push outward. Same thing it happens here also. It pulls electron from one end and throws from other side. I'm giving you a like very broad analogy, but if you study a little bit more comprehensive physics in upcoming classes or maybe in your graduation, you will realize far more than this, right? The concept is far more complex than this, but for this standard you can think it like same thing what I'm saying, that battery will push electron from one end and throws out from another end. Also, if you read physics in your higher classes, you will realize this electric field is not just due to battery, it is also due to the conductor itself. Yes, and this aligns this time. And why is that? We will discuss maybe after the completion of chapter. But for now, you can ignore that part. It is concept of higher physics. So, in this case, we know electron will experience some force F, and because of low accumulation of charge, it cannot or it will not produce their own induced electric field. right? And even though there is some force, electron will still not stop moving randomly. Can you tell me why? Because the temperature will be still above 0 Kelvin, and that means the thermal energy is providing kinetic energy to electron. So electron is still going to move here and there pretty much randomly, and because of this random motion, the motion of electron will not be that smooth. But what makes it different from other cases, that in this case, even though electron is still moving randomly, there is a little push on electron which is in opposite direction of electric field created by battery, which does what? Even after the random motion, it pushes electron a little bit in opposite direction of electric field created by battery, which causes it to move in the opposite direction of electric field created by battery. And the velocity, or the average velocity by which it moves in direction opposite of electric field created by battery, it is known as your drift velocity. Still, it is moving pretty much randomly. So, if you pick any electron and try to understand the motion, like for one-on-one electron, you will see somewhat like this. Again, it is old theory, not the new one, but if you again have a little bit idea from higher physics, or you might have read or heard somewhere, that you will realize actually electron cannot collide to kernels. It is just an analogy to understand it. And I would like you to think why electron cannot actually collide to kernels. I will let you think. If you know the answer, you can comment. Okay. But for now, for just a little bit of basic understanding, or should I say from 12th standard, you can imagine that they are actually colliding. Got it? So this electron will be moving randomly, and again there is electric field due to battery in this direction. It will be moving randomly, and because of this random motion, it will be colliding with kernels, and this collision will be continuous. And this collision will have some purpose, which we'll study in just few classes later. So here you can see, after many collisions, electron, what makes it different from the other cases. If you remember the previous two cases, after many collisions, the initial and final position of electron was nearly same, means there was nearly zero displacement, so average velocity was 0. But here you can see, even though there is many collisions, it is making a little bit of displacement, which is in direction opposite of electric field. Got it? So this displacement is due to your battery, and we will call it net displacement, and for now I am calling it lambda average also. Okay, so what is lambda here? So the distance between between any successive collision is known as your lambda. Lambda 1, lambda 2, lambda 3, and so on. This will be our lambda. So what is lambda? It is distance between two successive collisions. Displacement between two successive collisions. Right? Similarly, between two collisions there will be some time taken. That time taken is your tau 1, tau 2, tau 3, and so on. So this will be our tau n. So what is tau? Tau is time taken between two successive collisions. Right? And similarly, before collision it must be moving with some velocity. Let's call it v1 velocity, v2 velocity, and so on. This will be our vn velocity. So if you see the net displacement will be our lambda net, or also it will be known as your average mean free path. Average mean free path. How do we calculate this? So this will be our lambda 1, lambda 2, lambda 3 and lambda n over n. Right? Similarly, the average time taken between two collisions will be our tau average, tau 1, tau 2, tau 3 and tau n over n. Right? So what is your drift velocity? If you see here, imagine here like there is electron and again the electric field due to battery is like this. So we know electron will experience force in this direction, but because it has also thermal energy, so it will do what? It will move very randomly from here to here, right? Very randomly, it will be going back and forth and making some very unpredictable motion, but still this unpredictable motion will lead the electron to move in the direction opposite of electric field. It is somewhat chaotic, you can make your own, but the funda is this, that electron will be constantly moving here and there, but the overall displacement will be in direction opposite of electric field. Are you getting it? You can think it like a puzzle also, like there is a maze or puzzle you have here. We can make it complicated or we can fill it out if you got too much of free time, right? I think I make it okay. So somewhat like puzzle, and this will be your final end and this will be your initial point. You can imagine this is like very wide. You can imagine like 100 kilometer or 10 kilometer square region or something like. You can imagine that, and imagine someone has to go from this to this point. Let's say this is just 2 kilometers, okay? Or for the sake of simplicity, let's say it is 10 meter only. But the maze is very complicated. So anyone who is entering, he will be constantly running or she will be constantly running here and there with very high velocity, or let's say 5 meter, 7 meter or 10 meter per second, right? But he or she will take some time to reach this point. Let's say they took 30 minutes to reach this point. So and imagine they cannot get tired and they are constantly moving at the speed of 10 meter per second. Even though their speed is 10 meter per second, but the time taken to reach from initial to final end will be your what? Imagine it is square, so it will be 10 root 2 over 30 times 60 meter per second, and you can compare. It is going to be comparatively smaller than the speed of the person who is entering the maze. And this is the concept. Electrons are constantly moving here and there, and they are constantly getting collided by kernels. So the speed by which it moves in direction opposite of electric field, that is very small. Even though the electron moves continuously in random direction at very high speed, but the velocity or the average velocity by which it moves in direction opposite of electric field, that is comparatively very less to the speed of electron. Got it? So the drift velocity, the formula of drift velocity is this. We will learn the formula also, but first from this all the theory we got the average, the formula of drift velocity is this.
Hey there.
Right. So what is average drift velocity? I will tell you again. You can write. The average velocity by which electron moves in the direction opposite of electric field created by battery, that is our drift velocity. And the magnitude of drift velocity is nearly 10 raised to 1 minus 4 meter per second. And if you remember, speed of electron was 10 raised to power 6 meter per second. That means the speed by which electron moves is very high, but the velocity, the average velocity by which it moves in direction opposite of electron is very small because of constant collision. Got it? So we can write the definition of drift velocity. Got it? So this is our drift velocity. Got it? So all of you understood? Now if you see the picture, you will realize why this drift velocity. If you see the picture and from the definition, you will realize drift velocity is just average velocity, and average velocity you can also calculate it like this. It is v1 velocity plus v2 velocity plus v3 and so on. Okay, and overhead, and this will be approximately 10⁻⁻4 meter per second. Okay, so if you remember, this is looking similar to what we have done in case 2. In case 1, their average velocity was coming out to be approximately 0. But here you can see the average velocity by which it is moving in any direction, or here direction opposite of electric field is coming out to be non-zero. Because here average velocity is non-zero, the net current will also be non-zero. Got it? So even though it is moving constantly in random direction, still it is making somewhat progressive direction opposite of electric field. Got it? And it is all happening due to what? Battery. So battery doing what is so special battery doing that the average velocity is not coming out to be 0? The first thing battery is doing, that it is not letting charge to get accumulated here, and because it is not letting charge to get accumulated here, so what you can see, if it is not letting charge to get accumulated here, so the charge is experiencing force, right, which is different than other previous two cases, because in previous two cases the net force on charge was 0. This is the special thing about this is special thing happening here in contrast of previous two cases. You can take a picture, you can write all this, and then this definition also. So due to battery, what we are having, the E induced is nearly 0, and because E induced is nearly 0, so E net is just what? Electric field created by battery. Right? And what will be the force on an electron? Right? So force will be what? Q times E net, and Q will be just what? Charge of electron, and E will be what? Electric field of battery. And you can see the electric field of battery is in right, and the electron has negative charge, so the direction of force and direction of electric field will be opposite. That is being signified by the help of minus. So the acceleration of an electron will become what? Force over mass of electron. That is our this. So this is the thing which is different from other two cases, that F net is 0, or sorry, F net is non-zero, and there is some acceleration also, and F and A, they are both in same direction, and it is in direction opposite of electric field created by battery. This is why the electrons has non-zero average velocity. Got it? So because of this, we understood the average velocity was non-zero. So now we'll write U average. If you remember, U average we are picking from previous case. U average means the average velocity before battery. Okay. So before battery we are making it U, and we'll write V average. What is V average? Which is also here drift velocity. So this is what? After battery. Right? So remember this case. And if you remember, acceleration is coming out to be what? Constant value. Why constant? Because Why constant? Because what we are assuming that the dimensions of conductor is constant, right? So electric field is like this, right? So the potential difference is what? Minus E dot L, right? So electric field is just what? dV over L, and imagine that battery can supply constant potential, so electric field will become constant, and E is already constant, mass of E is already constant, so this whole thing becomes constant. So if acceleration of each electron is constant, we can simply apply what? Equation of motion. Means if you go back from the previous diagram, the velocity v1, v2, v3 or up to vn can be written in terms of u1 and acceleration and tau, and that's what we are going to do here. So we can write v1 means final velocity will be your what? Initial velocity plus acceleration times time, right? So same goes for v2 also. Right, and we can do, so we can also write for up to Vn. So Vn can be written as what? Like this. Right, correct. So what we are trying to find? Average velocity, right? Final average velocity, that is also drift velocity. So that will be your what? This is v1 vector plus v2 vector plus v3 vector up to vn vector over, and now you can plug the values. You will get what? u1 vector plus a tau1 plus u2 vector a tau2 and un vector plus a tau1 over, and now we can do what? We can write it more in more systematic order, like u1 vector plus u2 vector plus u3 vector up to un over n, and here we can take a common for, because acceleration of each electron is going to be same. Tau1, tau2, tau3 and tau1 over and correct. So if you remember, this is just what? Average initial average velocity of electron, means average velocity of electron before battery, which is approaching to be what? If you remember, this was approaching to be what? 0, because if there is no battery, there will be no enough force, or there will be no extra push which will move electron in a particular direction. So this whole thing can become your what? This whole thing will be what? 0. So we will be left with that. And what is tau1 plus tau2 plus tau3 up to tau1 over n? That is just your average relaxation time. So we can simply write this like this. So Vd and A is what? We just calculated a bit more bit earlier. So we got this formula, and here you can see there is negative also, which is just signifying that average velocity of electron will be in opposite direction of electron fed by battery. That is our final formula of drift velocity, and you can see here drift velocity has been written in terms of electric field. We can use this formula also, previous formula, to find the drift velocity, but for that it is that lambda average and tau average, it depends on many factors like material, temperature. So most of the time this value has to be given, then only you can use, but this value can be used. hold on, I have done a little mistake. Here I should write mass of electron. Now it's fine. Okay, because acceleration was right. So this value we can calculate far more easier, because again, but still they have to give you tau average. Electric field can be calculated with the help of potential difference and mass of electron, charge of electron is known. Still you can see there is we have still one ambiguity here, tau average. So what we are going to do about this, we will just we will talk about this. First let's see relation of Vd with potential difference. It's nothing new, because we have taken the potential difference to be constant, so I can write del V equals to what, minus E dot L, and because of diagram dot if you remove you will get cos 0, so E can be written as minus del V over L, and if you plug you will get, you can put modulus. So you will get what? Right, and we can calculate, we have derived the relation of Vd with potential difference. Got it? Okay. Now we will write Vd in more popular form, which is a little bit more easy to calculate if things are given. Again, few things has to be given, like free electron density. That means we are going to derive, or we are going to establish relation between drift velocity and current. Right? So this is we are deriving. For this we will okay, we will take temperature to be constant. I'll tell you why. Okay. Hold on. Okay, so we have one conductor. It is only one conductor, but we have pictures of same conductor at two different times. Okay, so you can imagine there is some wires, and here the potential is higher. So this is high potential, and this is your low potential. Right, high volt and low volt. So it will create what? Some electric field in this direction, correct? And because we have taken identical conductor, this is at T1 time and this is at T2 time, same conductor, so they will have same metal, same physical properties, and we have taken, we are going to take N. If you remember N from previous classes, N is your free electron density. For example, copper it is 8.64 into 10 to the 28 per meter cube. So free electron density is N. And what we are trying to establish, what is the relation between Vd and I. And if you remember, what is I? I is dq over dt. We are talking about instantaneous current, right? I is dq over dt, where dq is what? charge flown in dt time from given section. See, this particular section which is mentioned in both the picture, it is our given cross section, and we will do what? First we'll evaluate how much charge will flow in dt time from the given section, right? And we'll just divide by dt, or we'll see how it will go, and that's how we'll find current, and somehow we'll hope that this relation can establish something with vd. Alright, so dq is what? Charge flown in dt time from given section. Got it? So dq is what? Charge flown in dt time from given section. Got it? And how we can calculate charge? If I know how many electrons has been flown from this section in dt time, I can just multiply that number by charge of electron. I will get the charge. So let's say x be the number. Let x be the number of electrons flown in dt time from given section. Correct? So total charge, so I can write our total charge will be just what? X time E. Correct? Okay. So now the electrons, I will draw the free electrons. Okay. So the electron which is present in the marked section or given section, I am representing by with different color. Okay. From the picture, I hope that you can realize little, right, what I am implying. Right. So you can see from the picture that this particular colored or differently colored electron has moved in left direction, because this is, we are saying T1 time, this is afterwards T2 time. So you can see from the picture it has been moved by some distance, right? And because we know the average velocity by which it moves in direction opposite of electric field, that is Vd, right? Got it? And let's say the cross section of this conductor is A. Okay. So how much distance it would have traveled in this two time? Let's say the difference between time T2 and T1 is very small. So T2 minus T1 is dt. So now this time is satisfying that values, right? So if I'm saying this, like the time difference between these two pictures is dt. So what I'm implying here? So how much distance electron has been traveled in dt time, right? So distance will be our what? Velocity into time. So I can safely say that this distance is going to be Vd dt, right? And this is already, we talked about the area of cross section is A. So the given section has volume of dV, I can write, which is, or you can write V also if you want. dV by, I'll tell you, volume will be what? Area into length. So A times VD dt. And why we are interested about volume? I will tell you, because we have what? Free electron density, which is constant. So that means if I take complete conductor, then the number of electron over total volume, or if I say very small section of the conductor also, then free electron present in that section over that volume will remain same. That means the number of electron which has been flown from the given section in dt time, we have already said it to be x. So I can write n will be x over volume, right? So x will be just your what? N times the volume, which is A times Vd dt. Correct? The moment we got the number of electron, then I can say the total charge which we were interested to calculate will be just what? E times x, right? So that is right? Correct? Now if you remember, current is what? Current is what? Your dq or dt means the amount of charge which has been flown in dt time, that is dq or dt, and we have already found the value of dq, that is E times n into A into Vd times dt, right? And dt is also there, we can cancel out dt over dt. Remember, dt does not has to be 0, right? Because the moment you will make it exactly 0, you will not get anything, because it will not divide, it is very close to 0. Got it? So if we simplify, we will get the formula, which is E and A dd, and we can write in more appropriate way, so we can remember also. So we got I equals to V now. That's how you can remember it. That's our relation between I and drift velocity, and this is our cross section, and its free electron density is charge of electron. Most of the time free electron density is given, or we have to remember for particular metals. So with the help of this formula, it is pretty easy to calculate our drift velocity. And one more thing, remember that if electron is flowing in this direction, Vd is in this direction, our current will be in this direction. So if you are if you are confused about the direction of drift velocity, just remember the direction of drift velocity will be opposite of current, and that's our relation. In next class we will be talking about the Ohm's law and resistivity.